today the lecture is about, again, statistical patterns of turbulence. It's the second part, follow up to yesterday's lecture. And just to remind the setting, so yesterday we were dealing with the Navier-Stokes equation. Subject to some dissipation and forcing, supplemented, of course, by the incompressibility condition. And the observation was that as nu goes to 0, F prescribed, typically solutions look like they behave as stochastic processes. Look like stochastic processes. And typically, with this kind of graph, or if you plot the velocity with respect to time, for example, at one point, it looks random, yet it also looks very reproducible. And so this is what we want to describe. Describe the average, describe the law of the velocity field as nu goes to 0. And so in order to address this question, we discussed a framework, which is the K41 framework. Which states that under, which is a set of 3 hypotheses, that states that essentially in the limit when nu goes to 0, statistical symmetries are restored in a statistical sense. So symmetries of the Navier-Stokes hold in a statistical sense. So this is Navier-Stokes. And by symmetries, we mean essentially the fourth symmetry, the translation in space, translation in time, rotation, and scaling. Okay? So, yes?
Are these also symmetries for the Euler equation?
So, yes. Basically, the idea is very basic. So that's you have this equation. When you put nu goes to 0, formally you have basically those sets of symmetries. So what you're saying is, okay, I will try to put the symmetries of the Euler to describe the Navier-Stokes when nu goes to 0. So this is the essence of it. And actually, if you want to look at it a bit in more details, those 3 guys are symmetries of the Navier-Stokes. And this guy is not a symmetry of the Navier-Stokes, it's only a symmetry of the Euler. So, so the idea is that we want to restore those symmetries. So symmetries of the neighbor. And so there are two other hypotheses. Hypothesis is that scaling symmetry holds for a unique exponent h. So we remember the scaling symmetry was a symmetry where you transform space, you transform time, and you transform u. And this is parameterized by an exponent which looks like an older exponent. And the third symmetry is h equal 1/3. And that's the K41 framework. Okay. Now the question that we want to address is K41 valid? Okay, or reasonable, rather? And how to test it? And so there are two remarks that can be made. So we argued on last time that essentially the first three symmetries look to be pretty okay. Okay, in the sense that apparently translations plus rotation, okay, in the sense that if we look at exactly like those kind of quantities where we are looking at a velocity fluctuating, then those points are not subject to, they do not depend on the scaling. And typically when we plot either ui, the PDF of ui along this direction, or the PDF of ux along this direction, we observe the same thing. So if there is a problem, or if there is something to check, it relates to the scaling symmetry. And it is exactly the topic of today's lecture, which will be for today intermittency or the statistical breaking of scale invariance. And so first, again, let's observe. So what does it mean to have a scale invariance? So in this framework, it's so it is formulated in a here in a sufficiently loose way. But basically, what we have in mind that statistics of the velocity field, such as the one we saw yesterday, so this kind of thing, do not depend on scale at which it is looked at. So the important word, of course, is this concept of scale. We have to make it emerge. And perhaps a useful point of reference to understand what we are talking about is to look at situations where scale invariance is very visual. And so this is an example which is not from turbulence. It's an example that comes from statistical physics, which relates to statistical scale invariance at a critical point. So what we are going to do, so those pictures are realization of the Ising model at critical temperature. And to understand what it's about, it's better to see the video. It's very short. Again, because I think it's so nice. So here the idea is that we have patterns which are not exactly the same, but which look statistically identical at different scales, and it's impossible to, from the observation of a magnified observation of this scale, it's impossible to know at which scale we are. So this is a very visual example. And we may ask, okay, what about turbulence? So this is an example here where so it's a simulation which is a bit larger than the one we discussed the other day, yesterday. And it's the same game. You have a picture of a quantity which is here, which relates to the vorticity on the left, and it's magnified on the right. And here, I mean, it's very. It seems to be very different than in the Ising model, because when we see those two pictures, it seems clear that one is smaller than the other. They look different, in a sense, that. This picture here is full of all. So there is some kind of patchiness here, which clearly is a signature that what's happening at the small scale is not what's happening at the large scale. So this is what we want to describe. And in fact, we need to ask, we need to try to formalize a framework. Because the K41 framework applies technically in the limit of nu goes to 0. Okay. Well, this simulation is a simulation which has a finite Reynolds number, so it has a finite viscosity. So first problem. And the second problem, so first problem. So how to test K41 at fixed nu. Small, but positive. This is the first question. And a related question, which is related to the formulation of the K41 framework, means that the symmetries are supposed to hold for L for a scale which is sufficiently small. Only so for L sufficiently small. And so the question is, what does that mean? What does that mean? And so so the question is how to test K41, and the related question is what does scale mean? And to formalize those two ideas, we will need a concept, and this concept will be the concept of inertial range. So here I will try to provide a formalization of this K41 framework so in order to test it. And so in order to formalize it, I will propose a definition of something that I will call a new hit process. What's a new hit process? It will simply be only be a process which, at least for finite U, will satisfy the K41 framework. Or more precisely, it is a process. So if we have an underlying probability space. Okay, and so a new hit process, will be a process. U will be something like a process which will be parameterized by space-time and the realization, where X is in R cube, T is greater than 0, and omega in ensemble realization. Such that essentially U as is equivalently low to a certain so that low of U is mu certain density, okay? With the following properties. Mu nu is statistically is stationary homogeneous and isotropic. Okay. It is sufficiently ergodic. And in fact, what I will require is only that the two correlation length will be finite, in the sense that in particular, if we define a correlation length based on the gradients, it will be something like delta U of the old delta U of X is nu. The law of nu and average with respect to to nu will be denoted without the nu. Phi of u omega e u of omega. Okay, so I will require this guy here, which is an integral for x smaller than r when r goes to infinity, divided by delta u square is finite. So eta, so this is essentially, this represents the eta correlation length of one component of the gradient, typically. So that's why there is a cube here because we're in 3 dimensions, but of, say, dx ux, for example, in practice. And the second quantity that I want to be finite will be L, which I will take with the same kind of definition, which will be the limit as r goes to infinity of the integral with x smaller than r of u0 dot f bar of x. I take some absolute value divided by what's happening here at 0. Okay. And so this I will require that it is small. It is finite. And in particular, I will take that equal to 1 without a loss of generality. And I just need to define what is this guy. And this guy, f bar, is simply f of x plus f of minus x divided by 2. This is technical, but basically, this represents the correlation length of the applied force. Okay, so we are forcing, and the requirement that this is finite means that we are injecting energy at a finite scale, and as we were discussing, we can prescribe this correlation length to be finite, and we can also prescribe without loss of generality that this guy here is also finite. Okay, it's will equal to 1, and this represents so U0 F0 represents the energy input. And this we later assume epsilon equal 1. Prescribed, so we know what we are putting. And of course, so I have my stochastic process. I know the law. I require it to be sufficiently ergodic. And of course, the last condition that I should write is that with probability 1, T, the sample path, solve and the Union-Stokes equation. Okay, strongly. So you see so you understand the idea. So I'm trying to formalize this K41 framework in the context of the forced Navier-Stokes equation with finite viscosity. So I just assume that I have solutions can be described in terms of Stokes process with a certain law that has that satisfy all the statistical invariants but the scale invariants of the K41 framework. That this measure has some good erodic property, and that, okay, pathwise I am solving whatever sense you want the Navier-Stokes equation. So this can be, for instance, either the realization of the noise or initial condition. Okay. And so now, with that in mind, we can write down the following, which will be the scale-by-scale budget. Scale-by-scale budget. Which is an exact relation under those hypotheses, which basically tells you that if U is a new hit, then the following there is a budget that holds. In particular, this budget reads there is a certain functional of the velocity field at a certain observable scale, x. So this is the scale. Which is equal to minus nu times the correlation of the gradient in space, plus essentially this guy over there, the correlation of the forcing. Okay. Now this is this is a triviality unless we specify what du of x is on the other side, and what this guy is a complicated functional. And d of u it's minus 1/4 of the divergence with respect to x, the scale separation, of the average of a correlation that has delta u at scale x square times delta u at scale x. Well, in all of those rating, of course, u of x is a shorthand for u of x0. T equals 0. And delta u of x, it means only the velocity at position x minus the velocity at position 0 times 0. So there is the nice thing about this expression is that it ties three quantities. two quantities here, which relate to energy sink and an energy input. This is what it is. And the fourth quantity here is a quantity which involves the scale at which we are looking. And this scale is precisely given by this guy. Okay. So in the literature, this kind of relation can be seen as maybe it can be referred to as a steady state Karman Monin Howard equation. And its derivation, it's slightly painful but useful. So I will just sketch how this kind of relation can emerge out of the Navier-Stokes equation, because it will be really useful in order to understand what it means. So let's try. So the starting point. So I will use some shorthands. Shorthands. So I will have. I will write. I will consider the Navier-Stokes equation at position x, and at position x prime equal small x plus big X. Okay. We are. It's a bit like in UNESCO. Everyone is called X. Okay. And I will rewrite u prime of A equal the velocity field at u of x prime A that solve the LS equation. And all the prime quantity are relate to this new position. And so the starting point is just to write down the equation which is satisfied by both equations. So UA and U prime A satisfy the Navier-Stokes equation, which is for UA. So I'm using Einstein notation here to be able to make some computation. So UJ A plus DI P equals mu DJJ UI plus FI. So this is the first one. This is for U. The second one is the same with prime everywhere. U prime J, U prime J, U prime A plus U prime A. U prime IP equals mu derivative prime prime U prime A plus F prime I. And so what we can remark is that derivative with respect to I is d over dxi, and this is also the derivative with respect to the x prime I. So here I can erase those guys. Okay. I have my two equations. So what I will do is a very simple game. I will just multiply the first one by U prime A. Multiply the second one by UI. Then I'm summing. And I will take average. This is what I will do. So if we do that, what we get is the following. We get that dt of ui u prime I, this is the first term, plus u prime ui uj ui plus u prime j u prime I. This is the second term. Okay. Then you have the term involving the gradients. The term involving the gradients. It's u prime I di pi plus u I di d prime equal the right hand side. Okay. So this is so I will call it the left hand side. So the right hand side we will deal with it later. So in this expression, it's clear that this term is 0 by stationarity. By stationarity of the measure, so basically this guy does not depend on time. And that this guy also is 0. Why? Essentially because of homogeneity. Plus incompressibility condition, which is the I ui is u prime I u prime I u prime I ui equals 0. Okay? So we are left with this term here. It's already good. And this we call, so this is what we have. So this means that the left-hand side, we are just going to massage this guy a little bit. And so the good way to do it is to change the derivative here. So we make an integration by parts. And we will get the derivative with respect to j of ui u prime I uj. Yes, minus ui uj of uj u prime I. Okay, so this term becomes this term, and then you keep this term plus ui u prime j uj u prime j. Okay, and again this guy is 0 by homogeneity. This is what we have, and so this we keep in mind. And the magic comes now, because it's really a piece of magic, that we are going to, on the other hand, we observe that D, which is the quantity which was erased here, so the quantity involved in the scale-by-scale balance, which is D of xi times delta u square delta ui equal to certain thing. So we just have to expand this guy. So this is a u prime. So this is okay. So this is u prime j minus uj u prime j minus uj times u prime I minus ui. Okay. Now we just need to expand what's inside. And there will be some terms. U prime j, u prime j, a minus u prime j, y, chuk, u prime j, u prime I plus u prime j, uj, ui. So I have expanded with respect to this variable. Now to get the other one, I just copy this line, but changing the sign in the first variable. J I plus uj I plus uj u prime I minus uj j ui. Minus sign here. It's a lot of terms. So the observation will be the following one. That it's a lot of terms, but a lot of them vanish. So this one here, and this one here will vanish by let's remove this guy for now. Okay, that's very detailed. So averaging this guy and averaging this guy, they will cancel out. So in particular, so this is now I need to put brackets everywhere. So this one and this one cancel. So modulity. Okay, and so I am left with 6 terms. Okay, this is where now I take my d, what I wanted, and I take a derivation with respect to xi. Okay, so the idea is that when we divide with respect to x to the separation, so I will put this guy. I want to put this guy inside, essentially. And so what this operator applies only to the primed field. So, and this is the trick to make this work. So if you write it down, is that this, the D here, it is, so I will put, so those two terms are cancelled. I will just write the one I have. The first one, I put the derivative and it applies to this guy here. So it's ui, uj, ai of u prime j. Okay, this one will apply to this guy, minus uj ui di of u prime I, apply to this one, plus I u prime j ui uj, and the other one minus uj di u prime j u prime I plus u prime here. Yes. Plus uj ui ei of u prime j plus uj di of u prime I. Sixth term. So now we'll just investigate the term. So here we have a di u prime I. This is 0 by incompressibility. Okay, and top, there should be another one which varies by homogeneity here. It is this one, yes. This one is 0 by homogeneity. And then we are left with essentially twice the LHS, which is here. We can recognize the patterns. So ui, uj, di of u prime j is one of those guys. It is this one here. It's ui, uj. Because of incompressibility, this guy can be taken out. So this is exactly this guy. This guy here is u prime j, u prime I, di. So u prime j there could be an error. But in the end, what you get, if you are careful with the indices, is that you get exactly minus twice the left-hand side. And so this is minus 2d. D was a functional which was derived previously. And then you repeat the same game with the right-hand side, and you will get essentially the budget equation. So repeat the game. Repeat the game for the right-hand side, and you get the budget equation, which is this guy here, is equal to minus mu ux u0 plus u0 f of x. And d is minus 1/4 the divergence with respect to x of delta u square delta u. And we make a break now, and after the break, we are going to investigate the consequence of this budget on the notion of inertial range and on the way we can use this information to probe the presence or not of scale invariance in simulations which are inherently simulations which have only a small but non-vanishing viscosity. Okay. So now we have this budget equation. So we have this budget equation. So we call it Kalman Haworth-Bonner, KHM. Now, from KHM to scale by scale. Budget. What we are going to do is just integrate this relation integrate the Kalman-Haworth-Bonner steady state equation on both sides for a separation x below a given observation scale. Then what we have is the following. Then we get so the integral of d. So this we are going to call voilà. Yes. So we get on the one hand, we can call pi of L is the integral of d of x smaller than L. Okay. And here we have a divergence here, which appears. That is the integral for x smaller than L of a divergence operator times delta u squared times delta u of x. This depends on x only, sorry. And so this, you can write down that this as a surface integral. And so this will be the integral for x equal L of delta u squared delta u. Yes. And so this will be delta u parallel. So if you are integrating, you expect this is x. What appears here is just a longitudinal component. And so this, there is a nice formula. So if we can also express this as an average, essentially. And so this is minus. So if we assume yeah. So if we assume the isotropy, this guy does not depend on L anymore. And so what we are left with is the average of this guy over L divided by the volume of the sphere. for x equals L times the PL square. Okay, so here I have an integral, so I divide it by the surface of the sphere, and I multiply the surface of the sphere, so like this I express as an average with respect to the surface. Now I do the same thing for the two other terms. Yes.
Brackets spatial average or?
Okay. So I will use a shorthand. So in this expression, this bracket is really an ensemble average. Okay, it's an ensemble average with respect to the measure that defines the new heat function. Okay. So then what I will, so I'm taking this expression and then I'm further averaging with respect to a given prescribed scale. So what it means, so the notation phi for say x, for example, this will be in fact the integral for x smaller than L divided by the volume of the ball for 4/3 of P L cube, okay, times the average with respect to nu. So this is the ensemble average. Yeah. So basically, so here with this notation, it's just maybe it's bad notation. So we should put we should have in mind that you have two averaging process. You have you take only the dispersion which are small, and then you also have nu here or nu here. Okay. Thank you for this remark. Okay. So that's the left-hand side. Okay. And so if I average, and so for the right-hand side, if I make this game, I will simply get 4/3 of PL cube times delta U of x, delta U of 0 average on x below L times minus nu plus 4/3 of PL cube times U0 F bar of x average with respect to some separation. Okay? So the interesting thing to notice here, I forgot. Yeah, minus 1/4. Minus 1/4. Minus PL all of 4. Okay, so now if we sum up everything, we will have that so this is PIL, yes. So now if I okay, and then this by L, we can also divide everything by this quantity. So what will we get in the end is that delta U square, delta U parallel, average of X to L. And here we have a pi which is going to drop out. Something. Four missing again. So here there is so here it's the average with respect to x equal L. So the volume of the sphere in 3D is 4 pi L2. Okay. So this is minus 4 pi L2 that comes from the average, and the 1/4 which carries. Okay. Now we are good. So here what is left is just minus 3/4 minus 3/4L is equal to what's here? Minus nu delta ux delta u of 0 x smaller than L plus u0 f of x on x and L. And that's the budget. Okay. And here you see that what's appearing on the right-hand side are exactly the quantities which we required in the definition of the new hit statistical set to have finite correlation function, to have a finite correlation length. And this is what is going to play out right now. So this. So the interesting thing is that this quantity here depends only on the separation at a given scale. And this we may call, how will we call epsilon L. Okay? And then we are going to discuss the implication of this formula. So this is what we may call the scale-by-scale budget. So, what becomes of this formula? Say, let us now take L, the observation scale, very small with respect to eta, where eta, we remember eta is defined as, we call that eta is defined as the correlation length of the gradient. Delta u0 delta ux delta u0. Sorry. Okay, in our definition, and recall also that. We had a similar definition for integral scale, which was in terms of u0 f of x integral divided by r cube divided by u0 f0. Well, you have everywhere some limits. Okay, so that's our definition. So if L is very small with respect to compared to eta, L very small, then what we have is that this epsilon L is 0. It's 0. Why? Because so remember we are in a situation where we are where we are smooth. So L goes to 0. So this means that this will scale as L cube divided by L. So epsilon L will be 0. So it's of order of L2, if you want. And then you have those two terms. And those two terms, on the one hand, so since we are very small compared to the correlation length of the gradient, and we are very small compared to the correlation length of the forcing. Okay. We will assume eta smaller than L. Then you have 0 here. And here you have simply minus nu time the correlation at 0 plus u0 at 0. And this we call this 1. Consequence is that we obtain that nu, the dissipation, is equal to 1. Okay. First range. Second possibility, the second possibility is that eta is between, this time we take the observation scale larger than eta, but still smaller than the correlation scale of the forcing. Then what's happening? We have, on the left-hand side, we have epsilon L. And then we have this expression here. So if L is very small compared, if L is very large compared to eta, this means that it is as if when I'm integrating over L, I have this function appearing. So what we get in the end is simply delta u0 times eta cube. There's nu delta u0 square times eta cube. Okay? And for the other term, this one, I am in the same regime, so I will just get plus 1. Because of this condition, I know that this is 1 minus eta cube. Okay? So it's approximately equal to 1. Okay? So this means that in this range of scale, this expression on the left is constant. Is constant and is equal to the energy injection rate. Okay? The injection rate. And finally, we have the third the third range, which we can discuss. This time we have, if we take now the observation scale, which is very small compared to the correlation length of the forcing, then it's not eta cube which is going to appear, but what? That's a good question. Okay. There's a L cube here. And there, in that case, what's happening in this range will be simply epsilon L is equal to 1 minus eta over L cube. In other words, the dissipation, this quantity here, the transfer is vanishing. So in those two, in this picture, there is only one scale, okay, where epsilon L is constant, and this range here we refer to the range two. Eta is small compared to L and small compared to, and large compared to eta as the inertial scale, as the inertial range. Okay, and so in the inertial range, observation in this range epsilon L is equal to 1, and on the one side, and it's also equal to this quantity minus 3/4 of delta U square delta U parallel, which means that divided by L delta U square delta U parallel is minus 4/3 of L. Okay? And so here, this is exactly we have a scaling range. Scaling range where essentially delta U cube, delta U scale as L to the power 1/3.
The inertial range, that gradient is the actual gradient, or?
Yeah. It's the actual gradient. You take the gradient at the point. So this 0 here refers to the separation. So if you take 0 separation, it means that you are looking at the gradient of U square, and you average this over a box of. So if you do that, basically what pops out is just the value of this guy times and times this ratio. So yes, it's really a gradient. The gradient, a square average over the box, if you want. And so the question is, how can we estimate so let's make some estimate of eta. Okay, so on the one hand, you have at eta, this is true, and this is true. So you will have nu delta u square eta divided by eta square, estimation of the gradient, is equal to 1. And on the other hand, you have this, which is going to be true. It means delta u eta cube over eta equal 1. It's a machine argument. And from this, you get, if you multiply by the good power, that eta scales as nu to the power 3/4. Okay? So this means that as nu go to 0, eta go to 0. Okay, and this says this means that in principle for nu small enough, regime 1, so regime 1 is absent. Regime where L is very small compared to eta. This corresponds to what we may call the dissipative range. Regime 2, for which you have eta, the observation scale is between eta and 1. Then you observe scaling prescribed by K41, even if nu is not 0. And so this means that we can test K41 with experiments and simulation at nu, which is not vanishing. Which is kind of interesting. So it means that, okay, we have a theory which prescribes, which is an asymptotic theory. It tells you, okay, in the limit where everything goes to 0, this is what we should observe. And the consequence for experiments which have a finite viscosity means that there should exist a scaling range, so that basically when you observe all the properties of the velocity field on scales which are within the scaling range, we should observe the prediction of Kolmogorov. Question is, do we observe them? So remember, yesterday we yesterday we had argued that scale invariance reflects in a certain behavior for the structure function. Remember, scale invariance should impose that the structure function SP of L, which are defined as, for example, the velocity parallel to a certain power P, should scale as L to the power P H, is H presumably 1/3. Okay, and so this means that we have defined also, this means that this is equal to L to the power, say, zeta P, with zeta P equal PH. In particular, it imposes that, for example, S4 over S2 squared equal to L to the power psi 4 minus 2 psi 2. Should scale as, should be independent of the scale for L. Now we know where to look at between L and eta. Okay. Do we see this behavior? Do we see this behavior? And the answer is no. So this is the example that I discussed briefly yesterday, where basically we have gathered on the same graph experiments at various Reynolds number. So, and the data is rescaled so that the integral scale, L, is defined here, is exactly set to 1, and that eta is something which is on the left. Yeah. So the inertial range, where we expect Kolmogorov scaling to hold, is exactly this range here. And what we see, and it's pretty clear, is that we do not see the K41 scaling, and we see psi 4 minus 2 psi 2 for C equal to 0.1. Okay. Similarly, so this is this time an example taken from DNS. In DNS, so if we this time we scale not S4 but SP divided by so this is what's S3. This should behave as L to the power 3 over P, say P minus 1. Okay? So it should behave as L to the power 0 if psi P equal P over 3. Okay? And this, so it should be constant. And S3 is also proportional to L. And this is what we see. So if we plot F3, so on the left-hand side, this is the quantity here. Okay, so this scaling implies in particular that since S3 is scaling as L, so if scaling variance is satisfied, then this ratio should be independent of S3. It should appear as a straight line in log-log plot. And we see that this is the case only for P equal 3 here. But, this is a straight line here, which is by construction a flat line. And that scaling function, which are for P, which are smaller than 3, we see that the slope is increasing. And that for P, which is larger than 3, we see that the slope is decreasing. So this means that what we see, if we plot the zeta P as a function of P, we can see that it's there is a little bend. It's here, noticeable. There is a little bend. And the question is, how do we understand it? How do we understand it? And so we need to think. So there is a bend, so that the problem is not that. So if we think about Kolmogorov theory, so we had the three hypotheses. So statistical symmetries. Unique exponent H equal 1/3. Okay. Three hypotheses. So we say, okay, so the fact that it's bended here means that the problem is not so much this, this is a value which is okay, but it's the fact that we have prescribed a unique exponent. So whatever the value we would have chosen, we would have had a deviation from a pure straight line behavior. So this means that a priori, those two hypotheses are wrong. So not observed. Okay. So this means that this is not observed, with the exception that we have seen with the calculation that we have done previously that at least for the quantity H equal 1/3 is a reasonable choice because it is satisfied exactly in the inertial range by a third order structural function. But we know that essentially delta U squared, delta U parallel should scale as L. Okay, so we know that at least one of the zeta 3 should be 1, clearly. But apart from that, the value of this particular exponent does not prescribe at all the value of the other ones. And the question that we may ask is how can we have at least a heuristic understanding of this phenomenon? And I think we have just time to provide such a key. And this is the last model. I will propose a random H model. for intermittency. Or intermittency. So idea is very simple. It's adapted, but a bit different than what you can find in textbook. So idea is very similar to shell models, but even more simple. So idea that we are going to consider a toy model of intermittency. Well, essentially, we will have here some scales. Okay. So, and you have U0, U1, U2. UN, N considered as an integer is a stochastic process. Okay. For each value of n, we associate a length, which will be Ln is lambda to the power minus n, with lambda 0. And we also have for each of the, this is the length, and for each of the scale, we associate a typical turnover time to n, which should be nothing but Ln over Un. Okay? So those are, in a sense, two quantities which are what they are. And the question is what kind of dynamics that we are going to impose. So unlike what the models that were discussed by Alexei last week, we are not going to impose a deterministic dynamics, but we are just going to impose a very simple stochastic relation between those different scales. And we are going to make the choice that Un plus 1 will be lambda to the power minus Hn times Un, where H0, H1, Hn are also quantities which live here. Are independent random variables with a prescribed law we call H. Okay, it's yet to be specified. And so the rationale between this kind of dynamics is that this kind of dynamics exactly reproduce the scaling symmetries. Just to see that, it is not a proof, it's just a motivational argument. So rationale. You need to think as Un as a quantity which represents an increment, okay, at scale Ln and at time to n. Okay? So if we take, this is true for also n plus 1. So this, if we remember, so Ln plus 1 because of this relation, it's delta U of lambda minus 1 ln lambda ln over lambda tau n over lambda 1 minus hn. And this, by the statistical symmetry, should be exactly lambda minus hn of delta u ln tau n is lambda minus hn of un. So this choice is really to, so this dynamics, in that sense, it encodes the statistical symmetries of the Navier-Stokes, except that the Hn, which are being chosen, are not uniquely prescribed, and they follow a certain law. Okay. And when you do that, well, we can solve exactly this model. And just now we can compute the scaling exponent exactly. And just by realizing that un plus 1, un it's lambda minus